Okay. Looks like we're going. Cool. So today I want to dive into the downloader that Geth has. So I've looked at quite a bit what happens when a node starts up. So somewhere down the node starting up, it creates this new Ethereum object. It does so in a service. So there's an array of services that Geth offers, and in there is this Ethereum service. And it calls this new. So it does some stuff which we've kind of looked at a little bit, creating the database at chain data, creating this Ethereum structure, and down here it calls this new protocol manager. And in the new protocol manager, it passes this config.sync mode. And if we look over here, I've dumped my sync mode, not sync mode, my config. And the very second one is sync mode equals fast. And there's regular, fast, and light, I believe. The process sort of, like my understanding is, it'll download all the headers and all the blocks, and it will process every single one of them to get to the latest block, and that's when you can be a node and you can start processing. But to get to that point involves hundreds of gigabytes of data in a block, gigabytes of RAM to store the state, and it's almost too much for a regular computer to handle. And that's before even anything's been mined. But there's a lot of discussions because if you don't do this, you open yourself up to vectors, and it's like, what's the point of even having a blockchain if you're just going to download it and not sync it the correct way? It's like, well, you might as well just have a database, and you tell people to write to this database, and you have to trust who you downloaded it from. So I think there's back and forth of that. I personally believe that downloading the chain is the easiest way to do it. So this new protocol manager gets called. It gets past the sync mode. I don't really want to look at fast yet. I want to look at the full thing. But new protocol manager goes in here, and it goes new protocol manager. And it does in this Codebase kind of, and I think it's Go in general. There's just structures around structures to make things easier. Here we go. If mode dot, that's what we're talking about, the sync mode, equals downloader.fastsync, it sets this downloader to full sync. No, it sets this mode to downloader.fullsync, which is, I guess, an integer that's just wrapped around a name or something at this point. And this is all nothing yet, but a little bit further down, they call new downloader. So downloader.new. And this is the structure I want to look at today and dig into and figure out how does the blockchain in Geth get updated to the most recent block. So we've got this new here in downloader, this downloader.go package, which is, if we look at the file structure, there is ETH, and then there's a downloader. And yeah, I imagine that LES has one. No, it doesn't. That's kind of interesting because I feel like ETH and LES, from what I've read so far, are kind of like the same thing. Just the way that Ethereum's communicating and being stored. So for one to have it in the other, anyway, cool. Ethereum, ETH protocol has a downloader package built into it, and it's quite big, 1600 lines. So you can kind of tell this is where the meat of Geth is. And you listen to the chats they have about what the Ethereum's roadmap is, and it's all about trying to get downloading and updating your block to be as efficient as possible, because it's not. Like, for lack of a better word, like, you can download a 200 gigabyte file without too much trouble, but you're not downloading a 200 gigabyte file. You're downloading 200 gigabyte worth of files and then checking the integrity of every single one of them in relation to each other, which apparently takes like a week on a good computer and with good... Anyway, so cool. Calling new, there is a downloader structure. Which here it's and from what, looking 10 seconds into it, there's this state database that we've kind of been looking at. It's got your state, and it's got this blockchain, which is an interface below. And I think all they do is they write stuff to this interface. They're saying, get the hash, get this one, get the current hash, get the top header, read it, analyze it, use that to determine what's called next. And it's pretty much this blockchain and this light chain wraps everything, so that this downloader doesn't have to think. All it says is, give me this block, analyze the block, what do I have to do with the next block I download, and read it and check it according to the information in the header and the actual transactions and stuff. And it'll pass that, I imagine, to the proof of work algorithm or something. Who knows? Cool. So down here, they make the new downloader. The state database is passed in. Chain database. So up the top, we created new chain database, which stores everything, I guess. So I've been sort of trying to get my head around the databases in this software. And I'm like, oh, is there a separate database? Like, how does Ethereum store things? Well, not Ethereum, Geth store things. Because Ethereum protocol doesn't care about how things are stored. And I mean, is it like, you think of an SQL database and you're like, oh, the top database has different tables and it has different databases. And like, maybe there's a different database for the state, and maybe there's a different database for the transactions. But from what I've sort of getting at, and what I think is happening, is there's this chain database, which is what's passed here, which is what's made up here in this one, in the back end. They're called new chain database. Here. Create the database, which is chain data, which is what's stored at .ethereum /chain data. And then everything's just stored as a hash in that one database. I believe. So the block hash stores all the transactions. So you search the hash of the block, it gives you the list of transactions. You search the hash of the header, it gives you the header. You search the hash of the account for the state or something. It's all in the one database. They're just hashes. So the key changes. So we've called new, and everything's getting passed to it here. Say new peer set. I think a key thing in this bit is the list of peers. So up until this point, the node, I don't think, it might do it in here actually, because it's the Ethereum protocol, builds a list of of peers that you can question for things. And it doesn't do anything with them at this point. It just sort of like says, hello, can I have your information? So it sends a request to the peer just saying, this is what I can do, what can you do? And they get a response back, and that response is in this Etherum 63, I think it is. No. Now we've got spams. ETH protocol 63. Ethereum Wire protocol. Yeah, 63 is fast sync. So yeah, two peers connect, say hello, and they send a status message, and then it just gets saved. Up to this point, we read in here that says the one with the worst total difficulty asks the other peer for the full chain. And we haven't got to that part yet. So in the node, it's got its basic nodes. The ones that are saved in dump config here. I can't scroll that. Less. In these settings, in the default, they say bootstrap nodes, and it's got about 10 nodes for each software that's run. It's saved in there. They get called, and they do the hello shake messages, shake handshakes, blah. And that's all they do at this point. And it just keeps the list of, these are the peers, this is what their handshake has returned. And we know, it says here, it wants the one with the worst total difficulty asks the peer for the full chain of just block hashes. So, yay. Where does it do that? I don't know. So we got this peers, and it's searching new peer set. Is that in here? Don't know. If I go into ETH and under, that's going to be downloader. New peer set. In peer, how big is this file? 500 lines. So this downloader is like where the effort's being put. Peer connections. So this does nothing. This is just blank creating this. It's just a list of peers with some stuff for syncing and concurrency, so events. event handlers will be listening to those feeds and the lock. So that does nothing at this point. That's empty, which is good. Don't have to chase it too far. Okay, back to downloader. We've got a chain that gets passed in. And that's just, we haven't had a look at the blockchain yet, because that's also a 1600 word line file. But I mean, it's going to be, give me the header of this block, and you can search for it. And that, I imagine it's pretty straightforward. If you do tutorials on the internet, it's really not. The basic blockchain structure is not super complicated. It gets big because they want it to be, that's where the effort is. It's an important thing. But drop peer. This is a function to call if you've got a dodgy peer. If you've got a list of peers and you find one that's full of shit, you just call this function on it and it removes it. Header channel, body channel, receipt channel. What's a data pack, do you reckon? Next. It's a data packet. Cool, don't know. Where was I? Back here. So it just makes this, and it's blank at this point. It does nothing. So this handler creates a new one. And what does it do? I don't know yet. Fetcher.new. Download a fast sync. Manage a subprotocol. Protocol names. Message read writer. Manager.new peer. So this looks like it adds a subprotocol. So when the node starts up, it goes through all the protocols and calls this function, which is in the protocol, called run. And that's how the ETH service got created. But in here, where did downloader go? I was looking at 5 seconds ago. Downloader.new. Manager.downloader. Cool. So if this receives a handle peer, manager.handle. So down here, there's another function. I'm not sure if we looked at it. I might have looked at it separately on my own, but all it does is call read message on the peer's message. Downloader.new. Alright, so that's not going anywhere. So when we're in here, we're in new again. So they've called new protocol manager. They've got a new blockchain. They got ETH.protocol manager equals new.protocol manager. And we follow this down a little bit, and we see where Protocol Manager gets used. Now, so that's in mining. Protocols dot subprotocols. Okay, cool. So at some point, the Ethereum service gets started by a node. The node starts all the services, which includes Ethereum, and calls start. So there's a big array of all the services. Ethereum is one of them, and it calls start on them. And in there, it calls protocol manager.start. Which we're back in handler, I think. And this spins up what looks like 4 Go routines, a broadcast loop, a mined broadcast loop, the syncer, and a transaction sync loop. So what's the syncer, do we reckon? Transactions channel. So this is whenever transactions get added to this transaction pool. It's either it'll be listening. This when it says broadcast loop, I imagine it would be. This is where it gets a. Now that'd be in the function itself, so we'd have to dig into that, but I don't want to do that right now. But that'd be it. Whenever the program wants to send a message to a peer or to the network in whole, it would have all the stuff set up in here. But in this syncer, so syncer, it's not there. So another file called sync. So this is responsible for periodically syncing with the network, downloading the hashes and blocks, as well as handling the announcement. Header. What does that mean? Fetcher.start, fetcher.stop. Download or terminate. Start and ensure cleanup of synchronization methods. If there's a new peer channel, if there's a new peer, go pm.synchronize. If force sync, if not enough peers are present. So there's a best peer function in peers. In peer.go. Is that in downloader or just peer? There's a peer.go in absolutely every package in this one. Frustrating. So at 495, there's this best peer function, which takes, I would think of that as an array of peers that have some functions on them. This finds the max. And this is going to do what I imagine is a loop to find like a sort. Like we all seen really nice sorting graphics where it goes through a list, just an array with like 20 numbers, and saves the current best and then goes to the next, and if it's higher than it, then it will save it there. If not, it won't. So this is exactly what it's doing. We've got an array of peers, which is saved in ps.peers, and they're iterating over it. So they're going for everything in peers, which will return itself in P. If the total difficulty, which is the head, which is in the head of the best peer, and then it checks to make sure if there's something in nil. No, if there's not something in nil, it will do it the first time. So the first peer that gets checked will definitely get added to the best peers list. Example. If not, it will compare it against the best of the best peer. td.compare. Best td. And then it just returns the best one. Head. So it's just the header of the peer? I don't know what that means. Oh, it's just the SHA-3 hash of the peer's best owned block. So where's compare then? CMP. Not in here. Bugger. It might just be a string compare. Because that head is just a hash saved as a string. Maybe it doesn't. Or maybe it does. Yeah, I think you can. Yeah, there's a compare. But I don't know if it's CMP. Anyway, so you can compare two strings. So it might be just whatever hash is bigger. That doesn't sound right, but anyway, we don't want to dig into that. So we get the best owned blocks SHA-3 hash. And in sync, it's called get the best peer. PM peers best peer. Synchronize. So it's calling synchronize, but it's also... No, I want new peer channel, not force sync. But it's the same deal, isn't it? If the peers.length is less than the max peers, ignore it. So you get a new peer added, calls pm.synchronize with the best peer as a parameter to it. Fat Gary. The best place to start learning blockchain is probably just to, like, I'm not sure of your programming background, but there are a lot of tutorials on blockchain at the moment, and there are a lot of good ones. And it depends what language you're sort of working in at the moment. But this is a bad one. You want to program in Python blockchain tutorials. So there's stuff like this, where it's build your own blockchain. And it's like, again, I'm not sure if you're that comfortable with Python or anything, but like the first steps to kind of understanding blockchain is to realize like it's not that complicated. Like the underlying concepts are pretty straightforward, but you can find these build your own blockchain tutorials everywhere. And you do one, you do all of them. They're all the same. They're really just like you send a block, which is an array of strings which happen to be what a transaction is. I don't like Jupyter notebooks, but there's a Golang one that I actually did. What is it? Golang block. Build your own blockchain in Go. So the good thing about Go is that's the same thing that Geth is made out of. So I did this one. It's like, here they're defining a block, which is a timestamp, a data, previous block hash, and the hash. And this one's quite detailed in that I think there's like 8 types, and it goes as far as how the networking works. But the first one actually probably teaches you 90% of what is a blockchain, because they're really not that complicated. Like a block is just a timestamp with some data and a hash. You know, you set the hash to be the SHA hash and stuff. And the blockchain is just an array of blocks. You know, this is our first blockchain. I never thought it'd be so easy. There really isn't. There's not much to them. The terminology in the cryptos gets complicated, but it's mostly just like nerds just trying to prove how smart they are, really. Start with one of them. Just build your own. If you know any programming, like you'll figure it out. And then, especially if you start with a Go one, you can kind of jump into the Go Etherum Codebase pretty easily. And that's what I'm doing. I mean, I did that a couple months ago, and that's what I'm trying to get under now. So the downloader goes into this syncer, and the syncer tries to synchronize with the peers and calls this function. But that's exactly what I wanted. Here. Tries to sync up with our local blockchain with the remote peer. With the peer's best owned block. I don't think that's the right one. Where was I? Best peer. Oh, this returns a peer. It doesn't return the total difficulty. It's p.head and the best peer. So it saves the best peer. It compares the total difficulty of all the peers. And then calls synchronize on it, which is this one right below it. The protocol manager current block. So it goes and gets R's out of the blockchain. Just that blockchain gives you the current one. And the total difficulty is get total difficulty, which I imagine just returns a number. You compare the peer's head. Peer.head returns the head and the total difficulty. You compare the total difficulty to your total difficulty. And if it's greater than 0, then you don't have to update it. Cool. So what that's doing is exactly what it says here, and what you would kind of imagine. You've got a peer who may or may not have a better chain than you do, as in more recent, more up to date. They do that by comparing the total difficulty. So the newer chains have had more work on them, and that's increased the total difficulty. So you look at what your total difficulty is and another one's, and whoever's got the highest total difficulty means more work's been put into that chain, therefore it is the newest one. And also, if there's two that have the same block height, the more difficult one is the one that's you want to choose because more work's been put into it. So you're comparing the peers to yours. If the peers is not as old as yours, then you keep yours. You don't do anything. You return. Otherwise, you try to sync with the downloader. And this is where I want to get at. This is where all the effort's been put, and it's kind of hard. If fast sync is enabled, requested. So this just sets the mode. If the current block number equals 0 and the current fast block number is greater than 0, and this is exactly what happens if you look at mine at the moment. If I run geth, Control-C, somewhere in here, what it's doing is it's looking at the block number for the normal blocks, which are these full sync blocks, and it's also looking at the fast sync blocks you've got, and it's saying if the block number was 0 and the fast block number is not, that means fast sync was enabled at some point. And if I look at my geth output here, now I can't see it, somewhere in here, peer-to-peer networking, chain 1, that's the chain we're on, the main chain, homestead, DAO support true. And it'll tell you the block number, local node record. I can't see it. It's doing my head in. So, because I don't want to waste too much time screwing around, I'm still learning this stuff myself. There is in your blockchain, there is a block and there is a fast block, and they're different. They're not very different, but the fast block has less information. And because it's so hard to sync the Ethereum blockchain at the moment, it really doesn't want to do that anymore. So by default, Geth tries to sync with fast sync, which doesn't get as much information. It gets the headers maybe. So it increments what is going to be the fast block number, because that's what's being searched. And that's doing that. It's making sure that fast sync, it sets the mode fast sync if your chain. So if you set your mode to full sync, but you had originally started fast syncing and it hasn't got as far as downloading any current blocks, then it will switch it back to fast sync, which is not super exciting. Just determining whether fast sync is on. If mode equals fast sync, pm.blockchain.get total difficulty by hash. And then it compares the total difficulty of the fast blockchain. Boring. Not what we want to look at right now. We want to look at what it actually does. We want to see where it actually requests the information. So, download or synchronize. This is now the important function. But we're in a little synchronize. It has a little s. So this is kind of important, this port, I think. So the downloader calls synchronize. So sync. So tries to sync up our local blockchain with a remote peer. So peer ID, p head, p total difficulty. That was picked up before. So you get past this peer as this synchronize function. It gets the total difficulty, it gets the header information, and then it calls this downloader.synchronize, passes the mode in with it, which it spent so much effort determining, but passes the peer ID, the p head, the peer total difficulty. So here we are in the synchronize function, and it calls downloader.synchronize, which I think is going to do all of it. And this will actually call the stuff on the head, on the peer, excuse me. So what's it do? Synchronize. Little synchronize. SYNCHRONIZE. Here it is. We'll select the peer and use it for synchronizing. So at this point, they've passed the peer to it. They've said that this is the one with the highest difficulty, and it is higher than what we currently have in our blockchain at the moment. Synchronized mock for testing, I imagine. Make sure only one go routine is ever allowed past this point. So they don't want you calling synchronize 1,000 times and sending 1,000 spam messages to one of your peers. So only ever call this d.synchronizing. Compare and swap integer 32 is 0 and 1. And this is rather a complicated way of saying if there is a 1 in the synchronizing integer, which use an integer for this atomic stuff because concurrency is hard. But it's actually, this is just a boolean. This synchronizing is a boolean. So instead of saying if synchronizing equals false, return error busy, or is equals true, sorry. Blah. So that's what it is. Compare and sync 32 is just a fancy way of saying, look, that there's a 1 or a 0 in there. Defer, they store int32 into it. Defer meaning that they'll put a 0 in it when they've done it all, when this procedure closes. Then they look at the same thing for notified. Which I'm not sure. Post a user notification of the sync. Block synchronization started. So that'll pop up over here. There'd be an info, so there'd be an info here. There's a block synchronization started somewhere, which I've seen happen. Resetting the queue and the peer set. Cleaning it up. I think this is clearing stuff at the moment. So what is it doing? Reset the queue, peer set and wake channels. So wake channels to clean any internal leftover state. So they just want to make sure that everything's at 0 before they start requesting and looking at stuff. More super fun synchronization safety stuff. This is all just when you're talking over the internet with someone, it gets, and you just want to make sure that you got the requests are only going out once and the responses are coming back to the places they're waiting for them, and you're not blocking the program waiting for stuff. And that kind of gets hard, I guess. And then the very bottom, after it's done all this cleanup, it calls sync with peer and passes the exact same information, I believe. What's hash become? That's pass it. It says ID hash total difficulty mode. Downloader. Peers.peers. So you got your array of peers. There's an ID you've got for it, which is probably based on a 1 to 25 or something, because you got max 25. At some point, the hash of the peer got searched and you got an ID back. Unimportant, really. But they've now got the peer, which would be a structure, so you can call peer.get header or something like that, and that would send a request to the peer. So desync with peer is called next, and it starts with a block synchronization based on the hash chain from the specified peer and head hash. So they post start event to the whatever post is, downloader. Not sure. This is still not actually downloading it. Log, debug, synchronizing with the network. So if you make your geth verbal, geth, there's like a verbosity, I imagine, and you can turn up debug. Login verbosity 5. Geth T5. Ugh. Screwed it up. Verbos. Just dash verbosity. And it's got all this stuff. And somewhere in there, there'll be a synchronizing with network. Nope, I don't like that. I want 4. Debug. Couldn't add port map in. Removed dead node. Peer connected. We've got a peer connected. The handshake failed. Interesting. Dead node, dead node. Somewhere in here, give me a synchronizing with the network peer. More dead nodes. This might be why I have so much trouble synchronizing. Revalidated, recalculated quality of service. Cool. Handshake, added peer-to-peer, Ethereum peer connected, handshake failed. Ah, here we go. Where'd it go? Where'd it go? Ah, I lost it. Saw it. I saw a debug saying synchronizing with the network. Ah, cool. Exciting. Cool. Defer function start. Time.time. Synchronization terminated. Log debug. Elapsed. Ooh, wait, that's there. Synchronization terminated. Cool. So that's that calling that function there. So when this starts, it calls this defer function, which will call it when it stops, which is when it exits this function. Cool. It calls fetch height of P. So this request header by hash. Head. So this launches a request. And that request is just looking for the most recent header you have. And then it waits for a response. And then once it gets it, it will multiple headers for a single request. Stuff going wrong, stuff going wrong. Remote header identified. Hash number. Log.debug. Head.hash. And then I imagine it returns that head.hash. Return head. Cool. So back here, we've now got the head. This has actually sent out a request to the peer now. And it got the most. Height equals that. So it gets the height of the latest header. It calls d.find ancestor. And all this is going to do is it's going to look back through the chain until it finds what you and the peer have in common, I guess. But is that making a quest or not? Find ancestor. Tries to find a local common ancestor link of the local chain and a remote peer's blockchain. So figure out a valid range, full sync, blockchain.current block. Ah, interesting. So max fork ancestry. What this is doing by the looks of it is it goes into your block, gets your current block, and gets your current fast block. Or it sets the ceiling. And then request headers by number from count to 15. So it sets this from head equals ceiling if head equals greater than height. From equals head minus max headers fetch. So wherever that max headers fetch is set, might be 15 or so. Like maybe, who knows. Maybe it's in debug. Dump config. Max headers. Max peers. $192 amount of block headers to be fetched per retrieval request. Max block fetch is 128. Max hash fetch. So these are all hard coded into the downloader. So 192. So it takes your header, what you've got. They set this ceiling up here as the most recent one. They got the head equals it for some reason. If head is greater than height, head equals height. Which the height is passed in, so that's as high as the peers one, I guess. And they set this from to be minus 192. So you fetch in 192 headers before your most recent block header. Limit equals 2 times this divided by 16. So it's searching 15 at a time. And then it goes to here, and this is where it actually will request from the peer those 15 headers. So because this is done asynchronously, but this actually wants it to wait for the thing to finish. So it sets a timer. If there's no response before the timer, they cancel it. Now finished is actually if you externally send a finished message. So if the packet you receive is not from the peer, then you've received it from the correct peer. Not useful. If they gave something invalid, which are not headers, then so it's checking that what the peer sent back. If it sends back a header channel, it's legit. Make sure the peer's reply conforms to the request. So if they break the header chain, then like you've requested certain things. If they send back different things, then you're kind of like, nah, I don't want to listen to you because you're being malicious. Check if a common ancestor was found. So it goes through all the headers that have been sent back from the peer. If the headers is less than from, or the headers is greater than seal, continue. So you ignore the stuff that's not in your range. They get the hash of the header, they get the number. Then we look through our blockchain to check if that hash and that number exist. If it is known, even the future ones, if number is greater than height. So if the peer sends back a header that has a number of x, but the peer has said its height equals less than that, then the peer's being malicious. They're really checking stuff here. And in this process, number and hash is set. Once all this is done, you got the hash. If the head fetch already found an ancestor, return. So once it finds an ancestor, so it's found anything that you and the peer have in common. And I imagine the list is requested, so it starts at the top of your one, so your most recent block, and goes backwards. So the top one that's searched, first one, is your newest, then the last one. And once you've found an ancestor, they check if it's below allowance. I don't know what the allowance is. Less than floor. Floor was set probably according to some of those upper variables in the top of this file. Else they find a common ancestor. If there's not a common ancestor, they binary search over the chain. I don't want to delve into that right now, but it's just to save time. Instead of iterating one by one, they'll split it up and say, look, halfway through their one did exist, and then, you know, halfway through that, and it will find one more efficiently. I think that there's different types of searches, and it doesn't want to be iteratively going through one by one if you've got to go through 700,000 blocks or whatever it is, and they each take 10 minutes. So they split the chain in two and request to cross-check. I don't want to read that check-in because anyway, we've come to a point. They found a common ancestor, and they return it. So this whole function was just to find what is going to be the first block you're going to request from the peer by finding the common ancestor. So if I go back to n. So you found an ancestor. You take a lock. Origin equals where you're going to start looking. If the height is less than the origin, then you're going back to the origin. You're setting your chain stats height to what the origin is. So the sync has a heap of stats. Chain height is probably the most important. And they set the height to it. Is below any fast sync pivot point. I'm not sure what a fast sync pivot point is, but I imagine if you're less than, if the mode is fast sync, if you're less than min full blocks. Now let's look at that actually. $64. So you don't want to retrieve more than 64 full blocks. And I think that's just them trying to save themselves from doing so many full blocks because they're just super expensive. Or the other way around, that you must, when you're in fast sync, you must get the latest 64 blocks. Yeah, no, that makes more sense. Number of blocks to retrieve fully even in fast sync. So you got your blocks, you're up to 64 most recent blocks. Once it gets to that point, fast sync says we're actually going to read everything for these 64 blocks. And makes you go through it actually properly instead of just guessing, because that's how they get their security, is like they're saying, well, everything older than 64 blocks, if we do a couple checks of what other people have got, we should be fine. And then it does this queue prepare origin. So downloader has a queue, and this might be I don't know what prepare means. Initiate the sync using concurrent header and content retrieval algorithm. That looks important. Let's see what else is down here. No, everything's done in here. So the queue has a prepare in it. It says a download a queue. New queue. What's a queue, do you reckon? It's referred to a lot. Fetch parts. And there is a lot of files in this one. Where's new queue? New queue. It's not in this file. Bugger. Downloader. That's in queue. So there's a file called queue. And I imagine this is just going to be like an array that has a big list of here's the queue structure. Hashes that are either need fetching or being fetched. So you got a header hash. Task pool. This is quite lengthy. Damn it, that's 800 lines too. This whole downloader is huge. Even puts the blockchain main structure to shame. But imagine it's just got an array of items. New QUE. Lock. Makes a lock. Makes a heap of empty nothingness. Make prq.new. So it's got a new. What happens then? And it calls prepare on the queue. So there's a prepare. Configures the result cache to allow accepting and caching inbound fetch requests. Queue offset. So this does nothing. This is just settings. But it kind of looks like there'll be fetch requests posted onto this queue. So fetches equals an array of functions that return error. Fetch headers are always retrieved. Fetch bodies. Fetch receipts. Fetch process headers. Fetches equals append fetches. So they got this fetches, which are functions it calls fetch headers, fetch bodies, fetch receipts. So we're passing this fetches, I would imagine, to spawn sync. Maybe the queue, I believe, might take it or something. And then this fetch headers, fetch body, fetch receipt, fetch process headers gets called for what I imagine is every block. So they call spawn sync, which is right below it. And it takes a list of functions, and each of those functions, I imagine, is what they're calling on each block. Cancel workgroup add length of fetches. So there's 5 functions at the moment to be put onto this workgroup, and as you go through them, you deiterate it, I guess. So yeah, they go through the array. Function equals function. Spawn a new function in a different subroutine. Calling function and returning the result onto error C. And once it's done, you call cancel workgroup done, which reduces workgroup by 1. So for example, the first function was fetch headers. So we'd go in here, spawn a new process, call fetch headers. And it keeps retrieving head colors concurrently from the number. So you got the origin number, you got until the pivot, until no more returned. Cool. So I might actually call it there today. Because this is huge. I imagine I'm nowhere near even getting close to finishing. I'm line 466 of the downloader. Go home, touch, save.txt, vim save, and we go eth/downloader.go line 466, and that's where I'm going to pick up tomorrow. Now, thanks for watching. This is intense, this one. Who knows where it's going to go. Thanks, guys.